our today's session. And our speaker today is David Clancy from University of Wisconsin with a talk devoted to the central limit theorem for stochastic block model. Please.
Thanks for having me. It's a great pleasure. I'm here to talk about the central limit theorem for the stochastic block model. Although to kind of illustrate the proof, a lot of it is just going to be on the Erdős-Renyi, and I'll tell you how to kind of push this to the block model case. So I guess I want to start out with kind of the Erdős-Renyi random graph. So this is a graph on the vertices 1 through n. So that's what this bracket n is standing for, and each edge is included independently with some fixed probability p. And then I guess classical problems dating back to the early 60s is how large is the largest connected component as n tends to infinity for various choices of p. So for example, what values of Pn does there exist a component containing strictly positive proportion of all the vertices? And I guess more mathematically, we would write this as when do we have something of the form the lim of the number of vertices over n is bigger than epsilon, perhaps after taking some subsequential limit to deal with some tightness. Right? So this fraction is always going to be tight. So subsequential limits would always exist. Right? And this is kind of well known. In the Erdős-Renyi case, essentially, everything is known. So if we look at the edge probability p being this constant over n, or 1 minus e to the minus constant over n, these are essentially equivalent models. Then what we see is that as c passes from strictly less than 1 to 1 to strictly more than 1, there's this kind of double jump phenomena. Right? So whenever c is less than 1, the largest component is of order log of n. Whenever c is exactly 1, the largest component is of order n to the 2/3. And in fact, in both the c less than 1 and c equals 1, essentially all the finitely many largest components are all going to be of these orders. But whenever c is strictly bigger than 1, there's a unique giant component that is of macroscopic size. So in this case, there's a strictly positive constant rho that depends on our choice c, but it doesn't depend on whether or not we have these two edge probability parameters, such that the largest component, when you divide by n, converges in distribution to this number rho of c, which I wrote it slightly differently in the statement, but it's equivalent. And kind of useful for later on when I write the stochastic block model version is that this rho of c solves some fixed point equation. It's the non-zero solution to 1 minus e to the minus ct minus t is equal to 0. Right? So this is whenever c is bigger than 1, this is a concave function that has exactly two roots. 0 is always a root, and then rho of c is the other non-trivial root. And then I guess this first result is essentially the weak law of large numbers for the giant. When we want a central limit theorem, this kind of came slightly later in a work of Stepanov, although I don't believe this is the formulation that Stepanov wrote. But if we look at the size of the giant, minus the kind of number of vertices in that giant, divide by square root of n. So we look at square root of n fluctuations of the giant. This converges to a normal random variable with an explicitly computable mean and covariance. Well, the mean is 0, and we can explicitly compute the variance. But this is kind of like a very nice setting, right? The Erdős-Renyi random graph is extremely homogeneous. Essentially, we have one parameter that determines all the interactions. Kind of there's a massive generalization of this model where what we do is we kind of consider this abstract state space S, and then we assign each vertex an element in this state space. And then we define edge connections, or the probability of an edge connection, according to some kernel kappa, which has to be symmetric. But we imagine that each edge in the graph, or each possible edge in the graph, is included independently with probability 1 minus this kernel kappa evaluated at two locations corresponding to the vertices, xi and xj, and then we divide by n, so that we have roughly the same sparsity condition as in the Erdős-Renyi random graph that I mentioned before. And this is a super general model with soft edge constraints. We don't know exactly the degree of each vertex, but we know the degrees on average. And I guess technically how I wrote it here, the kernels kappa and these vectors x depend on n as well, but I'll just drop that to not overwhelm all the notation. And then there's this massive generalization by Bolobash, Janssen, and Riordan. And it says under some technical conditions on the state space S and kind of the behavior of these vectors x and some continuity requirements on the kernel kappa, then we can pick out a single parameter C, which is an operator norm of some integral operator defined by the kernel kappa and the limiting empirical measure mu, where if this constant C is bigger than 1, the largest connected component has order n many vertices with some explicitly computable like constant rho kappa mu. But whenever C is less than 1, the largest component is of order log of n. Okay. What happens at C equals 1 is a lot more delicate in this more general model. It essentially depends on you can think of it as like moments. Of course, it doesn't quite make sense in this abstract state space setting, but whenever S is, for example, the positive reals, this would be like a moment. Right. Unfortunately, this model is a bit too general as of now for me to say anything about a central limit theorem, so I'll restrict back to the stochastic block model. So this is kind of in between that fully general setting and the Erdős-Renyi case. So what do I mean by this? Well, now we're just going to fix the state space as some finite number of points, 1 through d. So these points 1 through d are the types of vertices that we're going to see. And we're going to give each vertex some type, and we're going to let ni be the number of vertices of each type I. Each of these ni's will themselves depend on the total number of vertices in the graph, but I'm not going to write that in the notation. And if we look back to this technical assumption that the empirical measure of the points xi converges to a measure mu, in this finite state space setting, that just means that the number of vertices of type I divided by the total number of vertices converges to a number mu I. And instead of having this general kernel, we can just write the kernel as a matrix, as a d by d matrix, because we have d types. And then the probability that a vertex u is connected to a vertex v is just 1 minus e to the minus kappa ij over n. So let me mention that as kappa increases, right, kappa ij increases, it is more likely for vertices of type I to be connected with vertices of type j and vice versa. For smaller values of kappa, it's less likely that they share edges. And we can translate these integral operators now into just matrix vector equations, right? So the integral operator t kappa of f now just becomes some matrix multiplication where we have the kernel k multiplied by the diagonal matrix determined by this vector mu multiplied by the column vector for f. And it's not too hard to convince yourself that the operator norm of this integral operator is simply just the Perron-Frobenius root of the matrix Kn. So in that case, this result by Bolobash-Janssen and Riordan can be translated into a much simpler statement, right? So if you have Km has Perron-Frobenius eigenvalue strictly bigger than 1, and the matrix Km is irreducible, then we can write down the number of vertices of each type as a vector. This is now a vector in Rd. We can divide by n, the number of total vertices in the graph, and this converges to an explicitly computable limit, which I'll write as m times rho, where this is a fixed point to a very similar equation that we saw before, except now it's 1 minus e to minus km times rho is equal to rho. And I will point out that this left-hand side is interpreted coordinate-wise. So we do this matrix vector multiplication, km rho, then we do exponentiation coordinate-wise in that vector. This is slightly stronger than the general result that I wrote before. So anyway, if we think that the stochastic block model is just a little bit more complicated than the Erdős-Renyi, we should expect that there should be a central limit theorem under some conditions. And that's what I'll try to present today, right? So if, in this case, kappa, this kernel, I'm just going to keep it constant for all n. And I'll present it with kappa I being strictly positive for all I. This is a technical condition that can be dropped, but the proof that I'll give today doesn't quite do that. We need Km to be irreducible, and I need some better control over the fluctuations of the number of vertices of each type, or I guess the proportion of vertices of each type with respect to mu. So I need Ni to be equal to the limiting proportion times n plus something of order square root of n, little o of square root of n. This correction is because I want to look at square root of n fluctuations for the giant. And if I don't have, if I have like n to the 2/3 fluctuation, then I can't really say anything about the square root of n fluctuations of the actual giant. Right. But anyway, what we can say is that the matrix K times the vector of all vertices, the type vector for the giant, minus whatever the limit should be, divided by square root of n, converges to a normal random variable with mean 0 and some explicitly computable covariance matrix, sigma. And this happens in D. I haven't written down sigma explicitly here. I do in the work that this is based on. It's a complicated matrix product, but shouldn't be that hard to see what it would be based on the structure of the proof that I give later. Before I go to kind of the general approach on how to prove these results, are there any questions?
No.
Cool. If at any point there's some questions, just stop me. Okay. So here's the main takeaway to prove a ton of things in random graphs, especially at the emergence of a giant component. Right? The key idea is to find a stochastic process Z that encodes the relevant information that you want to study. And instead of studying the kind of abstract model, you study the stochastic process and do some translation at the end. And luckily for the two models that I've mentioned, there are some tools that we can use to analyze them quite accurately. So I'm going to start off with the Erdős-Renyi case. So in this case, all vertices are of the same type. And what we're going to imagine is that we start with a single vertex V, and then we want to find a stochastic process that determines whether or not vertices are its neighbors. Right? So kind of just reminding, in this case, each vertex U is a neighbor independently with probability 1 minus e to the minus c over n. This happens for all vertices. Right? So 1 minus e to the minus c over n, this is essentially the CDF for an exponential random variable evaluated at a certain time. So what we're going to do is associate to each vertex I an exponential clock. And whenever that clock rings, when we're at vertex V, we're going to listen for a certain amount of time. And if an exponential clock rings, then we'll say that V is connected to whatever neighbor, whatever clock just rung. Right? And why will this work? Well, informally, it's just the probability that the exponential clock rings before time t, t being c over n, is precisely the probability that an edge appears in the random graph model. So this is really what's helping us in the kind of under the hood. Okay. So kind of here's the picture of how this works. Right? Now I'm just going to start with listening for vertex 1. Vertex 1 is going to listen for new arrivals at times psi j, and it will listen until time t equals c over n. Right? So since each vertex arrives independently, the probability that some arrival happens is precisely the probability that an edge appears in the graph. Right? So in this case, right, in this kind of toy realization, we hear arrival psi7 and psi3. So that means that in the graph, we'll add an edge between vertex 1 and vertex 3. But these are the only arrivals that we hear between 0 and c over n. So we only are going to add the edges between between the pairs 1, 7 and the pair 1, 3. Once we're done with vertex 1, we now go to one of the new neighbors that it finds. And just for concreteness, we'll go from the first vertex that arrives is the first one that's explored next. Right, so now we explore psi7. Oh, sorry, this is a typo. This should be 2c over n. Let me annotate this. This should be 2. Oops. Okay, I can't annotate it. Here. It should be 2c, 1c, and then 1c. Okay. So vertex 7 is also going to listen for duration c over n, right? And it could hear neighbors arriving. Right? So vertex 7 will listen from time 1 times c over n to time 2 c over n. And in this particular realization, I'll assume that it doesn't hear any neighbors. So I want to actually clear my drawings now. Right, so in this case, vertex 7 hears no neighbors, which so be it, that it could happen that no arrivals come during this interval. Right, so in that case, we are just going to go to the next vertex that we've kind of already heard arrive, but we haven't fully explored yet. So in this case, we go to vertex 3, and vertex 3 will listen from time 2c over n, which is when the previous vertex stops listening, to time 3c over n, which is when, which is just an additional c over n amount of time. Right, so some vertices could arrive, some couldn't, right? But in this case, if the probability that any vertex arrives, so psi11, this is kind of just a generic vertex, the probability that this arrives before time 3c over n, given all that we know before time 2c over n. So whenever we start listening for vertex 3 until when we finish, the probability that any vertex arrives is going to be 1 minus e to the minus c over n. And that's simply because of the memoryless property of exponentials, right? By time 2c over n, we know whether or not vertex 11 has arrived. And if it hasn't, well, then the probability that arrives in the next window of duration c over n, or sorry, c over n is just 1 minus e to the minus c over n, which is precisely the probability that an edge appears. So far, I've kind of described this process. Oh, sorry. Once vertex 11 appears, vertex 11 now has to listen for duration c over n. So this vertex would listen from time 3c over n to 4c over n. And in this kind of toy example, vertex 11 doesn't hear any neighbors arrive. So with this, we want to kind of, right now, I haven't described any like process. I've just described arrivals of exponential times. So how do we get an actual like random function that we can analyze? Well, we're just going to start at the value c over n, have a negative drift, but then have a jump of c over n at each arrival. So if we imagine what's happening here.
David, may I ask a question?
Mm-hmm.
So assume that you listen to Xi3
Mm-hmm.
and then Xi7 appears. Is it possible?
No. There's only going to be a single arrival for each.
One single arrival, and then you stop
yes.
listening. Okay.
Yeah. So what we're actually constructing under the hood is a spanning tree of the graph. Right? You can incorporate some additional randomness apart from these arrivals to incorporate edges, right? But so far that only works in the Erdős-Renyi case, or I guess it doesn't work in this stochastic block model case yet.
So assume that on the first interval from 0 to c over n, there are 3 arrivals. So say 3, 5, and 7. So you listen to 7, nothing happens. You go to 3, and you hear 11, say, and 13. You cannot hear.
Okay.
You cannot hear 5, 7, and so previous one. Yes.
Yeah. So in your example, let me just annotate this to make it a little bit more clear. So if we heard vertex 5 as well, right, we would add an if we heard vertex 5 here, Xi 5, we would add an edge between 1 and 5. And then when we're exploring 7, we can no longer hear 3 or 5 arrive because they've already appeared. Once we've explored 3, we cannot hear 5 or 7 arrive because we've already seen those.
And then we continue this procedure again and again. Okay, thanks.
Yeah. And I guess there is some subtlety on what spanning tree you want to connect. So the way I would do it is we would go 1, 7, 3, 5, and then 11. Right? But you could also go 1, 7, 5, 11, and then 5. And this is just the difference between a depth first or a breadth first construction.
Thanks.
I want to remove my annotations. All right. Cool. So what's the process that we're going to use? Well, we're going to start at time c over n, and we're going to just kind of have a negative drift so that if we start at c over n and we have a negative drift at unit slope, then if I can draw straight lines, then this would just mean that at time c over n, this straight line hits 0. So the time we would hit 0, if there were no arrivals, right, would be precisely the size of the connected component containing vertex 1 multiplied by this constant c over n. But in our example, there were 2 jumps. So we see these. These are height these are height c over n. Over here, this is also a height c over n. And then this is also a height c over n. And if we did the same game of just extending each of these lines until they hit 0, right? Well, then if we had never discovered vertex 3, we wouldn't have seen this second jump. Maybe let me use a different color. We wouldn't have seen this jump. So we would have hit 0 at time 2c over n, which would be c over n times the number of vertices in the component. And this kind of works for every other jump. So in this case, in this realization, we actually hit level 0 at time 4c over n, right? And we had 4 vertices in the connected component. So the connected component has c over n times the number of vertices in the connected component is precisely the time that we hit 0. And I guess here I should mention that we gave some arbitrary importance to the vertex 1, right? This jump at the beginning, c over n, is the vertex 1. Right? We don't really want to impose this artificial condition where vertex 1 has this importance. So what we can do is kind of forget about that jump and instead look at this sum. So let me go back here. This sum of indicators of the arrivals of these exponential arrivals starts from 2 through n. And it starts at 2 because this c over n corresponds to 1. If we forget about that c over n and just look at the actual empirical process, well, the sum of indicators for the arrivals, scaled by c over n, well, now almost surely it starts out with a negative drift below the horizontal axis. Oh. And then it will see its first jump. Okay? In this first jump up here, oops, annotate. This first jump is telling us that we've discovered a vertex, and we're going to explore the connected component containing that vertex. Okay? And then we do the same game that I described 2 slides ago, where we decrease at rate 1, we jump anytime a new vertex arrives, and then we keep on decreasing. So in this case, now it's the excursion intervals above the running minimum that describe the sizes of the connected components. And this is now the stochastic process that allows us to analyze things. Right? So let me kind of write down symbolically what this encoding does, is that the excursions above minimum describe the components of the graph, scaled by this factor of c over n, or by taking kind of rotating our heads 90 degrees and looking backwards through the screen, we can look at the inverse function of this running infimum to have the jumps of the first hitting times of levels.
So is that the compensated Poissonian process multiplied by the constant?
No, not quite. So
because you have n. Mm-hmm. I see vertices.
Yeah. If this were an infinite sum, so actually no. So what we can imagine is that each vertex j has a Poisson process, right? But we only care about the first jump of the Poisson process. So once that Poisson process jumps, we kill it, right? So in this case, it's I guess it could be like an inhomogeneous Poisson process whose rate depends on kind of the past history of the process.
Thanks.
So we have this translation. Connected components relate to kind of these excursion intervals or the jumps of the first hitting time. Right. So there's this wonderful theorem by Vladimir, that I'm only mentioning some consequence of it, is that if we order all the connected components of, order all the sizes of the connected components of the Erdős-Renyi random graph from smallest to largest, the one with the most vertices, second most vertices, and so on, with ties broken arbitrarily, then the largest connected component is going to be the size of the largest jump of this first hitting time process. The size of the second largest component will be the second largest jump. Size of the third largest component will be the third largest jump, and so on, up to this multiplicative factor of C over n. And the C over n is coming from the parameter p that we chose. All right.
I'm sorry, and what is t?
T is the first hitting time of the running impedance. Yeah. So I guess actually the way I wrote it here, this should be a left continuous process. So these jumps should be t of y plus minus t of y. So what does this mean? Well, if we do a simulation now, it's actually super easy in Python to run simulations with independent exponential random variables. So if we run a simulation for here, I believe n is equal to 20,000, and this constant c is equal to 1.2. Well, what we see is that if I could zoom in, if I could zoom in on the left endpoint, oh no. Okay. Okay, if I could zoom in on this left endpoint, we'd see that it starts decreasing immediately, but then it starts to be above zero fairly quickly. So it's going to be strictly positive pretty quickly, right? And it'll be strictly positive until sometime in the future. Right? And then it seems to, once it hits this, it decreases fairly rapidly. So informally at this point, we can think of from time zero through time whenever the excursion comes back. This is roughly C over n times the size of the largest component. Right? It's not exactly this, that we start exploring the connected component at some very small time after zero, but to a first order approximation, we can treat that as zero. Right. So how do we can actually use this to get a weak law of large numbers fairly easily. So we can turn this process Z that we saw before into something that we can analyze, essentially the first graduate probability course that you take. We have a constant C times the empirical CDF of a bunch of IID. Plot that here. Well, in blue, we have the fluctuations of this process Z around, and I don't know how viewable it is, but in green, this is just the true limiting function, C, 1 minus e to the minus t minus t. And it's not too hard to convince yourself using kind of real analysis that the size of the largest component, right, C times the size of the largest component divided by n. Well, we already know that this is equal in distribution to the size of the largest excursion of Z and T, and this should be approximately the length of the longest excursion of the limiting deterministic function, right, up to some order 1 error. And we can actually compute exactly what this term is, and it ends up being C times rho of C, where rho of C is the first root, first non-negative root, the only non-negative root of 1 minus e to the minus ct minus t. So this is how just a very simple stochastic process gets you the weak law of large, a weak law of large numbers for the giant of the Erdős-Renyi random problem. And you can use this for slightly more inhomogeneous models as well, but this works quite well for the Erdős-Renyi. But how do we turn this into a CLT? Right now I have a weak law of large numbers. How can you push this to a CLT, which is what we really want? Well, the idea is instead of using Clancy, which is just the law of large numbers, we're going to use Donskoy's theorem. So Donskoy's theorem tells us that if we look at the empirical CDF, we subtract off the true CDF, and we blow that difference up by a factor of square root of n, then this converges to a inhomogeneous Brownian bridge. Right? So in this case, it's just the standard Brownian bridge evaluated at 1 minus, evaluated at CDF. So kind of doing some hand waving with Skor-Hodge representation theorem and this uniform convergence above, or weak convergence in the Skor-Hodge space above, we can say that the process Z that we want to analyze is approximately the deterministic function that we saw from an application of Klippenko-Cantelli plus 1 over square root of n times a Gaussian process, right? Plus some negligible error. And in fact, the KMT theorem tells us under some coupling exactly how big this error is. It's, I believe, log n over n. Right. So going back to the random graph setting, we know that the largest connected component is the longest excursion above past minimum of this process Zn. So we can write this longest excursion as a starting point Ln and an ending point Rn, and the size of the excursion is just the duration of the excursion is just Rn minus Ln. Right? So Ln is when we start exploring, Rn is when we stop exploring. Right? And it turns out that there's pretty good control over when we start exploring the giant. Essentially, we start the level at which we are when we start exploring any component is an exponential random variable with parameter the number of vertices in the connected component up to some multiplicative constants. Right, so that means that whenever we have order n many vertices, the level that we are whenever we start exploring a connected component is of order exponential n, right? And we have pretty good control over that. Right? So in particular, the central limit theorem that we want, the size of the largest component minus the limiting value blown up by a factor of square root of n, is essentially square root of n times the fluctuations of Rn around C rho of C, plus some negligible error. So going back to the application of Donskoy and Skor-Hodge representation, we have Z is some limiting deterministic function plus 1 over square root of n times some fluctuations. If we evaluate at t equals Rn and rearrange the top equation, well, we have square root of n times phi of Rn is something involving Zn that is order little o of 1 minus a Gaussian process evaluated at 1 minus e to the minus Rn plus something else of order little o of 1. And since C rho of C is a fixed point, since Rn converges, we have a weak law of large numbers for the value Rn. So after another application of Skor-Hodge representation, we can assume it holds almost surely. So Rn converges to this constant C times rho. Right? And this now gives us a kind of the square root of n fluctuations of phi of Rn. Okay? And it converges to some explicitly computable Gaussian random variable. Okay? And using the fact that C rho of C, this limiting value, is a fixed point of phi, it's a root of phi. We can say that we have square root of n fluctuations of phi of Rn around phi of C rho of C. right? And we have normal fluctuations. Right? And if you've taken an asymptotic statistics class kind of early on, you learn something called the delta method. Right? And it says that if you have a sequence of random variables, xn, right? So think of these as like test statistics, and you want to show, and you know that xn converges in distribution to a parameter theta, and you can prove some CLT type result. So you can show that square root of n times xn minus theta converges in distribution to some limiting random variable z. Right? Then applying any C1 function allows you to prove kind of fluctuations of g of xn minus g of theta. Right? And why is this true? Well, you just do a Taylor expansion, right, and control all the errors. But the key thing is that if this derivative is non-zero, then this statement is if and only if, because we just have the inverse function theorem. So going back here, we have a function, right, applied to a statistic Rn minus a function applied to a limiting value. Right? We can use this if and only if statement, provided that the derivative is non-zero at time, I guess theta here is C rho of C, right? To take this CLT for the function of Rn minus the function of the limit and turn it into a CLT for Rn minus the limit. And up to an order 1 error term, like in, a little of 1 error term, the left-hand side over here is precisely the CLT that we want for the giant. And this is how you can get the central limit theorem for the size of the giant or the Erdős-Rényi. And you can do this also for some inhomogeneous models that are like rank 1, if you know what those are. Right. Now, this works great for the type 1 case. So let me kind of give you an overview of how we can push this to the finite type case. So in the stochastic block model case, right, again, we have D many types. Each vertex, each type has n sub j many vertices of each type. And what we're going to do is attach exponential clocks to each of these type j vertices. But now I'm going to double index these exponential random variables. So L refers to the label within the class of type j vertices, and then J will refer to the type. Okay. And then kind of as before, I'm going to start exploring from an arbitrary vertex. And let's just say it's of type 2 so that we have some picture in it. Okay. So the idea is that we now keep track of several timelines at once. And I'm not going to go through the full encoding. I believe in a few weeks, Vlada Limic will talk a little bit more about this. But the idea is that we're starting exploring at a vertex of type 2. Okay. So we start exploring here. Okay. And this type 2 vertex is going to listen on one of each of the many kind of time intervals. So each horizontal line here is a slice of some time coordinate, right, that keeps track of all the vertices in that type, right? So the second line is the type 2 vertices, and how long will the type 2 vertex listen for new arrivals? Well, it's the parameter that describes the edge connection probability between those two types divided by n. So in this case, it's kappa 2, because it's a type 2 vertex listening on the type 2 interval, right, divided by n, because this is the scaling parameter that we want. But it also listens on the timeline for the type 1 vertices. And how long will it listen? Well, it listens for the edge connection probability parameter, kappa 1, 2, right? 1 because we're listening on the type 1 timeline, 2 because we're listening from the perspective of a type 2 vertex, and then we divide by n, again, for the sparsity parameter that we have. Right? And then we do a similar thing on timeline 3. And we do this for each of the timelines. And in this case, we kind of have the vertex, say vertex 1 of type 2. It hears 2 vertices, right? Vertex 7 of type 1 and vertex 4 of type 3. And it'll discover these 2 edges. Afterwards, we're going to do a very similar thing for vertex 7, comma 1, right? The vertex with label 7 of type 1. Right? And this will listen on these blue intervals. Right? So here it listens for time kappa 1, 1, the first one because we're on timeline 1, the second one because we have a vertex of type 1, right? And it listens for kappa 1, 1 over n, right? And it discovers this 2, comma 1 vertex. And then it also discovers a 2, comma 2 vertex whenever it listens on the second time interval. It doesn't discover anything on the third time interval, or timeline, I should be saying. And then this continues, right? We listen for some amount of time for the vertex 4, 3 on each of the timelines based on the class of the vertex and the timeline that we're on. Right? But the idea is that we can push this encoding, right, to the finitely many type case using very similar methods. Unfortunately, right, finding the stochastic process that encodes all this information in a relevant way is a bit hard to do. So I'm going to clear my drawings and go to the next slide. Right, so this is what I said. We're going to keep track of time now as a vector valued quantity. Right? So now it has d many coordinates for each of the d timelines that we have. Okay? Tj you can think of as the amount of time that's elapsed on the jth interval. And we're going to look at a very similar process, okay? Except now we look at d many of these processes. So what are we going to do? Well, we have this artificial term at the beginning, kappa 1 I2. Right? This 2 is because we're looking at the type, we started from a type 2 vertex. Right? And then this I is corresponding to the index here. And then we sum up over all the other types of essentially, right, this is, annotate again. This here is essentially the empirical process scaled from before. Right? So this is very similar to the previous.
But NJs,
now we have,
are they dependent?
Sorry?
NJs. Their
NJs,
sum is n?
Yeah, they sum up to n, yes. But yeah, these are just real, just integers now, deterministic. Yeah. But the idea is that we can use a now random field, right, that takes an RD value time input and spits out a vector in RD to encode the graph because of this nice little fact that there exists a unique time, right, t, that is vector valued, right, that is a root of this vector valued equation, like it's a simultaneous root for all coordinates, right, with the additional property that it is minimal, right, in the sense that if you give me any other root, right, simultaneous root, right, then for all indices Ti is bigger than the special vector coordinate capital Ti. So in some sense, it makes sense to call this T the infimum over the simultaneous solutions to hitting level 0. And it's not too hard to convince yourself that something like this should be true. Right? And why is that? Well, think about kind of what happens from the in the exploration. Right? So we start exploring, right? We're starting at height kappa 2, 2 over n and kappa 1, 2 over n. And then we start out at some non-trivial height. So we're going to have to hit 0 by increasing this negative drift some amount. So this forces Ti, right, to at least be kappa I2 over n, right, for all I. But then over these intervals, we've kind of discovered new vertices, right? And that causes jumps of the summation, right? So we have to elapse more time, right? And since everything in the setting is finite, right, you can essentially do an induction argument to show that at some point you have to hit 0. Right? And it turns out proving uniqueness uniqueness and the fact that it's minimal requires slightly more work, but it's still doable. Right. Again, that previous description kind of prioritized the vertex that we started the exploration with. So we just forget that and include everything else. Okay. And this first hitting time argument, there's this nice theorem by Chaumont and Marleau that says essentially there's a well-defined vector-valued first hitting time, right, for simultaneous first hitting times of negative levels. And then in a joint work with Vitali and Vladimir, we were able to show that kind of in a more general setting, but you can encode the stochastic block model with this connection parameter kappa using the jumps of this first hitting time. Right? And the formulation that we have is, so think before that you had C times the size of the component. Now we have the connection kernel kappa times the vector of the component size. And I guess there is some algebra under the hood that converts the result that Vitaly, Vlad, and I proved into this setting, but it's essentially just algebra. Right. So now we can do very similar analysis to the type 1 case. Right? We look at the vector, each of the coordinate functions zi. Right? We can write this in terms of an empirical process scaled up by some constant nj. We can use sorry. Okay, I thought I had some pictures here. Yeah, but we can essentially give some approximations of what this limiting field will be, right? Using kind of the application of Donsker's theorem and Skorohod's representation from before. Right? So we can write kind of jointly for all j, each of these summands is going to be some limiting deterministic function plus square root of n fluctuations. Square root 1 over n fluctuations of a Gaussian process plus some negligible error. Once we scale by this nj over n, this becomes a mu j, and by our condition, our hypothesis that nj over n is approximately mu j plus some negligible error, we can absorb the error in the approximation of nj over n into the little o of one term on the side. Right. So kind of putting things together, we can essentially have a similar decomposition to the type 1 case. For each coordinate I, we can write zi of t is some deterministic function phi of I of t plus 1 over square root of n times a Gaussian process, now indexed by an RD valued time parameter, plus something that is negligible, right, of order little o of 1 over square root of n. Oh, yeah, here's where the pictures come up. Right. So it turns out that this function phi, the deterministic function that we have, has exactly two solutions in the scenario where the Perron-Frobenius eigenvalue of Km is bigger than 1 and Km is irreducible. If Km is not irreducible, it could have strictly more than two solutions. If the Perron-Frobenius eigenvalue is less than or equal to 1, it will only have one solution, right? And that solution is 0. Right? But there's going to be another non-trivial solution. So if I just plot kind of the indicator functions of where these coordinates are positive in kind of the T1, T2 plane, right? Kind of this this bottom right region is where phi2 is positive, but phi1 is negative. The top left region is where phi1 is positive, but phi2 is negative. The yellow region in the kind of bottom left is where both are positive, and the top right region in purple is where both are negative. And what we see is that they intersect at some point. All four regions intersect at some common point that is T naught. And that, in this two-dimensional case, is the kind of the non-trivial solution of a fixed point equation. And to kind of go through everything, we can essentially do the same game as before, right? We have a weak law of large numbers for the giant. We can convert this with a bit of algebra to saying that k times the vector c converges to this northeast point. We can do a Taylor expansion. Sorry, I'm going through this a bit quickly because of time, but we have Zn is equal to phi n plus a Gaussian process. So we can kind of create bound some error terms. So as before, the start of the observation window and the level at which we start that observation window are negligible, right? We can relate the fluctuations of phi of the ending of the excursion with phi of this deterministic quantity T naught. This gives us some central limit theorem for a function applied to the random variable we want to study. And then there's a generalization of the delta method to functions, vector valued functions. Right? If now we have vectors and some limiting vector valued parameter, the delta method applies, right? Provided, in the statement is if and only if, provided that the Jacobian, instead of the derivative, the Jacobian needs to be invertible. And that allows us to get a scaling limit for Rn minus the limiting point T naught. And we can get, we can convert that using the result of Vlada Vitali and I to a statement about the size of the largest component. And I guess, sorry for speeding through the end, but yeah, I can stay around for questions if there are.
Okay. So thank you very much for interesting talk. And maybe somebody have questions or comments, please.
I have a question. Actually, David, as I understood, like the general principle here, the idea is to reduce everything to the processes or to some process, and then get the central limit theorem for that process, and then go back. And my question is, if you would care also about how fast or about the rate of convergence, for instance, in terms of the weak topology, where you apply some function to your object, you compute the expectation. So here also it seems on the first step, when you make this link between the process and the random graphs, so you can, I mean, in the terms of the rate of convergence, you have also this identification. Somewhere you also use the Taylor expansion. Also, it seems that it should not influence on the rate of convergence. Actually, could you apply also this approach to reduce the rate of convergence for random graphs to the rate of convergence of the stochastic process?
I believe so. Right. So if you want to analyze the rate of convergence in the stochastic block model case, you would need more precise control over nj over n. Right? So kind of this general approach allows you to say whenever nj over n is a limiting value mu j plus a constant times 1 over square root of n, right? So beta j 1 over square root of n plus something of little o of square root of n. If you wanted to do some concentration result, you would have to state kind of exactly what that error term is, and then you would have to use a stronger coupling than just Donskoy's theorem. So kind of.
But actually, you don't need constants. You just need like how fast it converges, right? How fast the other terms converge.
Yeah. Yeah, but yeah. So I think you could use this KMT theorem, the Kumlash, Major, and Tuznadi theorem. Yeah. That gives you very precise control over over the empirical process minus the CDF scaled up by and some Brownian bridge, right? You blow up that difference and you have some nice control over that. I suspect you would be able to push some of these arguments, at least in the Erdős-Renyi case, under that coupling. In the stochastic block model case, I suspect it's a bit harder. Yeah, partly because as we have discussed separately, we need excursions. And in the real case, excursions are very nice. Yeah.
Okay, thank you.
Okay, some other questions, please. I also have question. Sometimes people discuss it not only the size of the components, but the complexity, the structure. So, for example, diameter, then index of complexity, and especially for index of complexity, we also can have some recurrent equations and some limit theorems, like it was done in book of Dromota, for example. So, what do you think? Can you apply your approach to this different characteristics of random graph?
So I'm not sure what complexity would mean in this case. Is it like the number of cycles in the graph?
No, this is some. We have connected component. We just have a sum where we summarize x, for example, lambda in minus distance between two vertices in these connected components. And of course, for such sum, if we have some recurrent tree or Erdős-Renyi, we can get some recurrent equations which occurs to have a limit when number of vertices tends to infinity under appropriate scaling, and we again get sometimes not processes but equation for distribution, limiting distribution functions, and so on. So I think that your approach also can be used for such characteristics.
For distances between vertices, yeah, there is this approach of height processes, right?
Yeah.
Where you can turn the encoding that I talked about before into kind of a process that measures distances from the vertex that you start exploring. As far as I'm aware, this works very well in the Erdős-Renyi case, in the critical regime where C is equal to 1. Okay. I think there is a result in the supercritical regime, but I'm not so familiar with how it works. I think you can describe kind of the limiting distribution of the distances in the giant from a fixed point. But this approach would be about fluctuations and how fluctuations of this kind of the Z process translates to fluctuations of the height process. That seems very difficult to do. I'm not saying it's impossible, but like the height process is done by a very weird functional of this process Z, and that seems hard to translate this Donsko's theorem approach.
I see.
Yeah, but it would be interesting if, I guess, we could get like a second order analysis.
This was the reason for my question. Yeah, because
Yeah.
it is very nice to have such a straightforward approach as you demonstrated. So it looks like when we have even we have non-Gaussian limit
Okay.
for those characteristics. We have non-Gaussian limit at all after even after scaling.
Okay.
So I think that must be some connection, but of course it is hard to say. Okay.
Yeah. Yeah, I'd be actually very interested to see if that can work. Yeah.
Okay. So maybe some other comments, questions, please. If not, thank you again very much for interesting talk, and hope to see you again at our seminar.
Yeah, thanks for having me.
For today, we finish our job, and Georgi, who will be the next speaker?
Next speaker is Andrei Ilyenko.
Okay. Again, central limit theorem, yes?
Strong limit theorems.
Oh, yeah. Okay, let's see. So thanks everybody, and see you next week. Bye.
Georgi. So I am the next speaker or another one?
No, you have in 2 weeks.
In 2 weeks. Oh, thanks.
Okay. Bye.
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 Goodbye.